Greetings everyone, my name is Matthew Clark and I'm a PhD candidate in the Department of Aeronautics and Astronautics at Stanford University. I'm a member of the Aerospace Design Lab, directed by Professor Juan Alonso, and today I'll be covering the prediction of the operational envelope of electric aircraft through robust battery cycle life modeling. And admittedly, this is a mouthful, so throughout the presentation I'll be covering key concepts including cycle modeling, thermal modeling, as well as aging and how it relates to predicting electric aircraft performance more robustly. This presentation is intended for the AIAA Aviation Conference for 2020. In this presentation, I will go over the following. I will first start with an overview, then I'll talk about battery modeling for aerospace applications. I'll follow that with flight profile simulations, then conclude with results, and then talk about the future work and findings that were very important in this study. So let's hit the ground rolling with the overview. And in this section, I'll cover some background, then I'll follow that with current state of battery modeling, lithium-ion technology, the motivation for this research, which is the NASA X57 project, and conclude with the research goals. Greenhouse gas emissions from transportation account for 29% of the total US emissions. These startling statistics make transportation the largest contributor of all measured economic sectors. With lightweight vehicles such as personal cars, taxis, and rideshare responsible for nearly 60% of emission producers in this sector, it is without question why the development of alternative fuels, hybrid and all-electric solutions has been centered around the automobile transportation. Despite only accounting for 9% of emissions within the transportation sector, projections indicate that aviation itself is the fastest growing industry and consequently cannot be overlooked. As a result, governments and private sectors are looking for ways to reduce carbon footprint through the use of biofuels and electrification. Only recently has there been a noticeable emphasis on reducing the carbon footprint within the aerospace sector. High energy and power density requirements, coupled with stringent safety margins compared to ground transportation, has plagued the development of electric aircraft. However, the advancement of battery technology has led to the development of many high energy density batteries, as well as potential cost savings, summarized in the table below, which presents a compelling case to transition away from dated internal combustion technology. Electric propulsion offers dramatically lower operational costs, while improving efficiency, commuting noise, propulsion system reliability, and safety through redundancy, as well as, like I said before, reducing greenhouse gases. This is particularly evident in general aviation aircraft, where the combination of poor aerodynamic and propulsion efficiencies coupled with high cost of low lead aviation fuel account for approximately 50% of operational costs. However, before I dive into any battery analysis, I want to take a couple steps back for the audience and start with some basic chemistry, atoms and ions. We all know that atoms in nature are stable. However, they want to achieve a more stable configuration by having a full outer shell, and they do this by bonding. They may either bond to themselves, such as oxygen and nitrogen in the atmosphere, or they could bond with other atoms, such as hydrogen and oxygen, to create water. Sometimes these reactions are violent, as shown below with sodium and water, and sometimes they're not. The process of achieving stability is simple, and it's done so by bonding. As you can see here, sodium bonds with chlorine by sharing electrons to form salt. So how does this relate to electric batteries? Well, within a battery itself, there are atoms which are constantly bonding to each other, and this release of electrons is how current is flown. Current flows through the battery cell. Keeping this in mind, let's look at the basic components of a battery. Starting from the left, you have a current collector, which carries electrons to the outer circuit. Then you have a negative electrode or a cathode, which is usually a metal oxide. And within this metal oxide, you can have lithium ions being deposited. Then you have a separator or electrolyte, which allows the movement of lithium ions from the negative electrode to the positive electrode, which is typically graphite. And then on the other side, we have another current collector, which receives the electrons. During discharge, lithium ions move from the negative electrode to the positive electrode through the electrolyte. Electrons move in the same direction, but take the longer path outside of the circuit, producing what we know as current. Conversely, during charging, lithium ions are removed from the positive electrode of the anode and make their way to the negative electrode through the electrolyte within the cell, and outside of the cell, electrons move in the opposite direction. So that's the basic principles of charging and discharging, and those two principles I will get back to later in the presentation when I talk about battery aging and degradation. The most common types of battery assemblies are pouch cells and cylindrical cells, and each have their own unique characteristics. Pouch cells are usually have a higher energy density. However, their soft outer shell makes them susceptible to external impact, and therefore they need to be covered or encased in a harder outer shell, which increases the weight. On the other hand, cylindrical cells are self-contained, and as a result, they're more commonly used in everyday applications, such as in mobile gadgets, toys, etc. And these cells are also cells used predominantly in electric vehicles as well as in aircraft. The durability of graphite with its long life cycle remains today as the best negative electrode. As a result, the major differences or the delimiter within lithium-ion batteries particularly comes at the positive electrode. As you can see here on the image to the right, we have a spider chart displaying the properties of different battery chemistries. We see here specific energy, specific power, energy density, power density, safety, etc. With high scores in safety, performance, and cycling, we see from the spider chart that lithium iron phosphate is the best chemistry of choice for large electric applications where weight is not a significant factor. However, in applications where weight is very sensitive, such as in aerospace applications, battery chemistry such as lithium nickel cobalt aluminum oxide, which is NCA, or lithium nickel manganese cobalt oxide, NMC, are preferred. In this presentation, I will dive particularly into these two chemistries with particular emphasis on the NMC chemistry. Now in practice, there are two main categories for characterizing the state of charge and the state of health of a lithium battery. State of charge is essentially how much energy a battery has in one particular cycle, and the state of health can be thought of as the state of the battery after X amount of cycles. Essentially, how well the battery performed at day 1 as opposed to day 100. The first method is a phase transition and an ion transport method that models electrochemical kinetics. However, this model is very computationally expensive and is not really suited for real-time applications. The second method, equivalent circuit models, which use power law relationships that encompass a limited range of parameters which can be obtained from experimentation. As shown below, experimentalists typically run experiments using accelerated aging tests. Then they use such tests such as the pulse polarization test to gather parameters for fitting, and then use discharge and charge models for a particular application. However, there are several shortcomings within the aerospace industry, as little to no emphasis has been placed on modeling battery life. There have been some studies that have shown to model battery cycling during or battery prediction or state of charge during a particular mission. However, little to no emphasis has been placed on modeling a battery throughout an entire mission over repeated use. As I said before, lithium ions are self-contained systems. However, the available energy diminishes with repeated cyclic use. Physical chemical mechanisms are enhanced by stress factors such as current severity or C rate, state of charge, overcharging, and discharging. Performance degrades mostly as a result of thermal stress due to internal resistances such as heat dissipation, as well as the solid electrolyte growth. And this is essentially a film around the graphite, as I shown before, or the graphite in the image of the battery, where the graphite is coated and as a result cannot attract lithium ions. In addition to that, overcharging has the ability to cause the exfoliation of the cathode, or the oxide layers in the cathode, reducing the ability for lithium ions to electronically attract the gaps. Now, what does this actually mean? Well, the repeated charging and discharging can essentially widen the gaps, and if you have large gaps, the ions cannot attract, and as a result, if you can't sustain the lithium ions, your total energy storage capacity. So with that being said, here lies my research goals. First is to outline the implementation of a discharge and aging model for lithium-ion batteries. Second is to detail the implementation of models into SWAV, a conceptual aircraft design environment used by ADL and many others, but maintained by Aerospace Design Lab. Third is to outline the procedure for predicting the cycle life of an electric aircraft using the flight profile and experimentally obtained parameters of characterizing aging, which I'll talk about in the future. And lastly is to identify the sensitivity of battery chemistry, rates of climb and descent, range on the discharge rate, cycle life, and state of health of the battery. So, with that being said, I'm going to shift gears to the second part of my presentation, which focuses on battery modeling for aerospace applications. And in this section, I'm going to cover three main areas: the electrical discharge model I plan to use, the thermal model, and lastly, the discharge model chosen for the NCA and NMC chemistries, which I mentioned before, was the Thevenin based model, which is a semi-empirical model that allows for the characterization of not only the steady state, but the transient responses. This is very critical for predicting the battery performance under high frequency load modulation needed to stabilize the aircraft during flight. As shown below, this comprises of four key components: the open circuit voltage, the ohmic resistance, the polarization resistance, which captures the internal resistances, as well as the polarization capacitance that describes and accounts for the transient responses during charging and discharging. Shown to the left now are the relationships for only the NMC chemistry from Panasonic and relationships by Zoo. You see here the internal resistances and the ohmic, as well as the polarization resistances, as well as the time constant, which is used to calculate the Thevenin capacitance. And these four relationships can be used to derive a simple ODE equation, which can be solved to determine the underload voltage, as seen. The thermal model, secondly, is a simple thermal model which uses the square of the current times the total resistances, and the heat generated can be used to determine the net power of the system, the net power produced by the system, which comprises of the heat generation through resistance heating, as well as the heat loss from convective heat transfer. Here, the cell mass was the mass of the 18650 cell, or the small cylindrical cells, which was 48 grams. The specific heat capacity, it was taken from literature, was around 837 joules per kilogram per Kelvin. The ambient temperature was around 20 degrees Celsius, and this actually changed in the experiments, and I will talk about this in the future. And then the heat transfer coefficient was the heat transfer coefficient modeled in a paper which talked about the optimal heat transfer coefficient for battery modeling within a battery management system. Before I talk about actual results of an entire mission, here I want to show you the comparison between the discharge and charge cycles of the NCA and NMC. These both chemistries are simple in gravimetric and volumetric energy densities. However, NMC chemistry had more literature on degradation. As a result, continuing on further in the presentation, I'm going to focus on the NMC chemistry for battery aging. Now the figure to the left, sorry, the figure to the right, which is temperature, shows that as initially during discharge, the temperature increases as the temperature increases and then attenuates as the equilibrium is reached. And I'll spend a little bit more time on the temperature relationships and the reason the temperature actually attenuates further in the study, in the conclusions. Next, we look at the aging model, and for this I employed an equivalent circuit-based model developed by Smallsteed, which uses physics-based principles and models them to experimental data to characterize aging. It consists of an impedance-based thermal electric model coupled with accepted metrics for predicting lithium-ion cell degradation. Here we see this model is made up of two parts: calendar aging and cycle aging. The electric current profile, ambient temperature, and the depths of discharge are used to determine stress factors caused by volumetric changes in the intercalation and deintercalation of lithium ions, which I spoke about earlier, which is essentially the ions bonding and releasing from the anode and the cathode structure during discharge and charge. The repeated cycling of the battery induces capacity loss and internal resistance growth, and therefore can be seen using the equations seen here. Now, putting it all together, the superposition of the calendar and cycle aging thus provides a total aging function of the capacity fade as well as the resistance growth. One thing to note here is that the capacity fade has a quadratic relationship with Q, or the charge throughput, and the charge throughput is essentially how much current has passed through the individual cell. However, the resistance growth has a linear relationship with the charge throughput. Here, T is time in days. Now, the following section, I'll go over some flight profile simulations. As previously mentioned, the motivation for this work was the NASA X-57 Maxwell project. This is NASA's first electric aircraft in over 20 years. It's an all-electric aircraft built to spur ahead the electric propulsion focused design as well as the airworthiness. And it was designed by modifying an Italian aircraft by an electric powertrain powered by lithium-ion batteries, as seen here. Now, there are 4 configurations that NASA spoke about. In this study, I'll be only focusing on the twin-engine high prop configuration. Study utilizes SWAV, an open source code developed by Aerospace Design Lab, and it involves the evaluation of mission points done by solving the equations of motions as well as the mechanical electrical equations representing the powertrain. And it's done by formulating residuals and driving that to 0, as shown below. The simulated flight profile consisted of 4 key components: a constant ascent rate, a constant speed at 25,000 feet, a constant descent rate segment, as well as the charging segment at the ground. This mission was simulated 4 times a day and for an entire calendar year. The taxi and the takeoff segments of the aircraft mission were omitted in this analysis. Before we look at the results for an entire year, let's look at what is happening within the battery for just one mission. The 2 plots on the left column are plots of the pack level, where you see the battery energy and below the battery voltages. And on the right, you have the cell level properties of the cell temperature as well as the C rate, or the current severity. 2 interesting things I want you to pay attention here. First of all is the cell temperatures, and see where the highest temperature occurs at the 45 degrees Celsius temperature occurs at the top of climb as well as in the charging. As well, notice that the current severity in the bottom right plot changes even though the mission segments are constant rate segments. From the previous slide, we get 2 main takeaways. First, the results from battery pack modeling suggest that the pack temperature linearly increases with the supplied current, but scales with thermal capacity. Using a similar submodule, module, and pack configuration of the F-57, it was discovered that each cell was exposed to small currents during takeoff, the most power-intensive phase of flight. The thermal model predicted a maximum temperature of 45 degrees Celsius, which occurred at the top of climb. Now, during charging, on the other hand, when the initial state of charge is low, the relationships previously mentioned predict high internal resistances, resulting physically in an initial stark increase in temperature. As the temperature increases, the resistance and the diffusion of ions increases, the internal resistances drop, resulting in a less thermal heat being created. And this can see as the voltage increases, the current or the C rate decreases, and as a result, the temperature starts to attenuate. The second key takeaway here is the reliance of, or the dependence of, a previous mission on the performance of flight segments of a subsequent mission. That is, throughout an aircraft's lifetime, the battery aging results in changes in voltage and currents to perform this similar maneuver. As a result, these simulations were computationally expensive. Moreover, if one wants to do any sort of optimization, the creation of a response surface is preferable. On to the results. Shown below is the prediction of the capacity fade and internal resistance growth of the NMC 18650 cell used by the aircraft over a calendar year in San Francisco. The ambient temperature used was the maximum daily temperature obtained from information from the National Center of Environmental Information. This is a subset of NOAA, and this is used in the thermal model. Two main takeaways here is that the initial energy capacity of the battery decreases by about 15%, and the internal resistance increases by about 20%. What this meant now was that if you look at on the image to the right, that the intended mission, which was from SFO to Sacramento at the initial first day, was reduced to about 70 miles, and as a result, after a year, the aircraft could not meet its requirements. The impact of the rate of climb on battery life was studied through the analysis of flight profiles with a combination of ascent and descent rates. A total of 9 combinations were created. As you can see here, the mission which characterizes the minimum battery degradation was one which had a high ascent rate and a low descent rate. This can be thought of as follows. Really, initially, at the beginning of the mission, at high SOC and open circuit and the load voltage, less current is required to produce the same amount of power required by the propellers. As a result, since the current is less, if you remember the equations of the battery aging, particularly the cycle aging parameters, which depend on the charge throughput, the small currents will reduce the charge through the battery, and as a result, the aging is less than at low SOCs where higher currents are required. Secondly, with regards to range, which we would expect, longer ranges will essentially cause the battery to degrade more. However, what is interesting to note here is that we see about a 5% increase in the resistance, a 5% decrease in the capacity per 10 miles, as well as a 2% increase in internal resistance. Now alone, these parameters are not significant. However, when used in conjunction with the energy consumption profile of the aircraft, response surfaces can subsequently be created to predict the exact time at which a repeated mission can no longer be executed, given the requirements of, let's say, a percentage SOC cutoff, as well as a nominal 10% range reserved flight segment. And this is where the power of this model comes into play. On to the last section, future work and conclusions. Future work includes devising a method to reduce the computational time of the model. As mentioned before, a 1-year simulation took about 6 days of CPU time. So this is very important if you want to incorporate this into an optimization loop. Secondly, a major assumption on this paper was the concept-specific heat capacity, or rather, was that the battery was made of a homogeneous material. Future work involves implementing a model which can predict the non-uniform thermal behavior within the battery, which allows us to predict the surface temperature of the battery and thus the heat transfer outside of the battery and into the battery pack. Thirdly, we would like to analyze the life of the X57 over a wide range of flight profiles, which each have a characteristic energy draw. And lastly, apply these methods to prediction of the battery life of non-conventional UAM vehicles, such as stop rotors, tilt wing and tilt rotors, as well as multi-rotor configurations. So in conclusion, we see here that robust battery modeling is a critical component in electric aircraft design, because the omission of cycle life studies can result in the overprediction, which can lead to aircraft failing to meet their requirements after a particular time period. The results from the study of the X57 for this particular mission indicate that battery life can fall as much as 15% after 1 calendar year. That concludes my presentation. Thank you.